Here we go. We're going to record. All right, here we go. Okay, it's day 3. I'm going to tell you right now, on Friday, I'm going to go ahead and have you come to your regular class hour, excuse me, for a real short little activity where we're going to learn about how to calculate stuff, okay? Now, I know on Friday you have some other things. Do you have with English, you have a MemBean assignment. Did you know that? And then Spanish, you're doing some little quiz thing online. And I think also with history, you're doing a little bit of collaborative stuff. But during science class on Friday, I just need you to come here just during this time, just for a real quick little thing with me. Okay. Hey, how many of you guys saw the International Space Station fly over last night? Now, if you saw it, you did? Good. It would have gone like this across the sky. Okay, and it was in the northern part of the sky. It wasn't very high up, so if there were trees and stuff or houses in your way, you might not have been able to see it. Sometimes it goes straight overhead and it's way, way brighter. I have seen it to where it's so bright you can actually see the solar panels on the side, which is really pretty cool. All right, so I got a question for you. How fast is the International Space Station going? All right, so just to think about this, look at this right here. So the space station is 254 miles above the Earth all the time, okay? Now, the radius of the Earth, you guys, is 3,958 miles. Now, it goes all the way around one time every 92 minutes. So that means if you're riding on the space station, every 92 minutes, you're going to see the sunrise. Okay, so they go through lots of days on the space station where it rises and sets. Okay, so if you go circumference, we know circumference is 2 pi r. So the radius would be this plus this. So 2 times pi times r means that they're going 26,456 miles every time they go around. 92 minutes is the same thing as 1.53 hours. So if you take 26,000 whatever divided by 1.5, you guys, that means they're going 17,000 miles an hour, which is about 5 miles a second. So like this, they just went 5 miles through outer space. It's possible one of you might someday be on that space station or an astronaut. It's likely, in fact. I had a kid back in Tennessee that wanted to be an astronaut. I've got one of my students from Collegiate. She's working in SpaceX. And another one of my students, he actually built stuff that went up in outer space too. And actually a third one also is building stuff that's going in outer space. So it's likely that you guys, some of you would want to do that someday. So that's kind of cool, I think. So I just wanted to tell you about that. I might have you look for the space station again. If you send me a little picture of it, then what I will do is I will give you an extra credit point. All right, so here we go. Let's look at this now. Okay, assignments that are due. Okay, today, that graph that looks like this, is supposed to be turned in, this graph right here is supposed to be turned in via Schoology today. If you need any help with that, come and see me during tutorial. Also, the rubber band video is supposed to be in Seesaw by Friday. If somebody needs direction on that, think about it like this. Thomas and Peyton did two good things. Thomas took a slingshot and shot a rock, and then he took the same slingshot, pulled it back the same distance, and shot a brick. Okay? So the brick wouldn't be able to go very far, right? All right, so it wouldn't accelerate. See, so that's all you really have to show. Peyton came up with the idea of using the rubber band, but he shot a ping pong ball, and then he shot a golf ball. Okay, would you see a dramatic difference in acceleration there? See, so something like that, be creative, okay? Now, if you need any help with that, come to tutorial. All right, now let's talk about this. Lunar lander time. Okay, now look, this is tricky. You've got to land in tight spaces and then take off and land again in a different place. And it's okay if you group chat with each other. Now let's look at this right here. Okay, when we look at this thing right here, I'm going to unpause it for a minute. I'm going to crash it. There we go. All right, now I'm going to reset it. Now, you guys, if you hit the space bar like this, it turns on and off the gas. Or you can hit the toggle bars. Up and down gives more or less force. I'm going to crash it. Ah, boom. Okay. You need to look over here. See this? This is the horizontal velocity and the vertical velocity. This is the range left to right, and this is the altitude. Here's the thrust in newtons. I want you to turn on these vectors right here, because if you turn on the vectors, okay, see if you turn on the vectors like that, it'll help you to understand how to score points. See right down here, this is your score, 15 points for that. You have to get 75. That's going to really be a pain to some of you. Some of you that like to play video games, this is going to be easy, all right? But some of you that don't play video games, this is going to be a pain, all right? But hey, what else are you doing? You're at home anyway, right? All right, here, so look at this right here. That might be a callous statement, sorry. Okay, so I sent you this email. This is where you're going to turn in your score. Here's a website for where to get to it. It's going to be, I certify on my honor that I got the score shown below. And so what you're going to do is you're going to paste your score right here. Okay, you got to get 75 if you're going to be able to get an A. If you get a pretty good score, I'll give you a B for it. You know, if you only get like a 5 or something, I might give you a pretty bad score. But I think if you try, I think you'll do well. Derek.
We're allowed to use extra credit points on it if we don't do well.
Yes. But keep on trying, you know, keep on trying. I think it's good for you because you'll learn how to look at the force vectors and figure it out, okay? All right. All right, now let's go back to this right here. Okay. So you guys, in your email, I sent you a dynamics worksheet. Could you open that up right now? Okay, you can put it in OneNote. You're gonna need to be able to write on this. It looks like this. There's a camera on the front of it. Okay, so go ahead and do that right now. Get to that, please. Hey, Skay, are you there?
Yes.
How come I can't see your screen?
Hold on.
It's so nice to see all your bright, shiny faces. There you go.
I may not be in bed.
What?
I may or may not be in bed.
I see a pillow. You're all looking good to me. Okay, so are you looking at that worksheet? Okay, here we go. So now, hey, everybody, the first question's about the camera, right? How many of you guys have seen a big camera like this, a really nice one? Everybody? Okay. How come professional photographers use that big old camera? All right, now think about this. This is in terms of Newton's 3 laws. The first law says for inertia, objects at rest want to stay at rest. Objects in motion want to stay in motion in a straight line. Okay, so why would they use a big camera like that? Yeah, Sam.
Better quality, more functions.
Yeah, way more functions, but there's something about Newton's laws. Derek.
Since it's a bigger camera, it won't shake as much.
That is exactly right. How many of you have taken pictures with your phone before? You take a picture and then when you look at it, it's all blurry. Have you done that? See, they use a big camera because a big camera, when they push the shutter, it won't shake. In fact, one of my nephews, he's a for the professional photographer for the Denver Broncos. You should see these gigantic cameras they have, and they're on a pole, right? And so when they take their pictures, they're crystal clear because the thing has a lot of inertia. You get that? So you need to write down on your worksheet right now. You need to write down that the big camera won't shake as much because it has so much inertia. So the pictures are clear. So write that in. Okay, second question. Now these are like 4 old worksheets. I just put them together so we could review. The second question. How many of you guys have ever used a meat cleaver? Have you, they let your parents let you do that? Or you chop stuff? Okay, Carter has. Why are meat cleavers so big? Why don't you just chop stuff with a butter knife?
Because the slam power.
The slam power. That's exactly right. Okay, to help you understand this, how many of you have ever swung an axe before? Have you ever swung an axe and chopped on a tree? Okay, good. What if I said, Sia, I want you to go outside and chop down that tree with a herring. Never mind, that's Monty Python. Chop down the largest tree in the forest with a butter knife. You'd go like this with a knife. You'd never do anything. Why do axes? Why do they have that big head on it? Because once you get the axe going, it wants to
Keep going.
keep going because of inertia. That's why they make meat cleavers so heavy, so that when you chop, it keeps going right through the food, the steak, the carrots, whatever. Okay, here's a trivia question. Okay, there is a professional chef that works at Wichita Collegiate Middle School, a teacher. Who is this person?
Mr. Vernon.
No? Do you know? It's Mr. Joe Gear. Okay. He's been trained as a chef. So I know he knows. Have you ever wondered how they keep from chopping their fingers off when they're going like that?
Well,
A glove? I don't know. All right. Okay, here we go. Look at the next question. Okay, the next question, it says, why is force a vector quantity? Okay, Tyler, why is force a vector? Because it has
direction and magnitude.
good. Because force is, you can have a force down or up or side to side. See, any quantity that has a direction with it is a vector. Good. All right. So write that in. Okay, bow 2. Bow. All right. So hey, bow, the next question says, if you tripled the mass of an object, what would happen to its acceleration? So if you keep the same force on it, but you triple its mass, what would happen?
It's harder to accelerate
Yeah, how much harder would it be to accelerate it? Give me a number.
3 times.
It would be 3 times harder, so the acceleration would be 1/3. Okay? So that next question right there, the acceleration rate would go down to 1/3. Okay? Hey, Phoebe, does your dad own a sports car?
No.
No? I would have thought he would have had a sports car.
No.
All right, so sports cars are really, really light, and they have big engines, okay? So think about this. What if you triple the force that you put on an object? What would happen to its acceleration rate?
it would triple.
It would triple. So that would be 3 times as much. So question number 1 is because they have direction. Question number 2 is 1/3. Question number 3 is 3 times. Have any of you guys ever ridden in a Ferrari before?
I want to very
Yeah.
badly.
There's several of our kids before that have had like Ferraris, and man, I tell you, they just are so powerful. Okay, here we go. Next question. The next question. What was this one about? I can't remember.
What's the acceleration of an object that moves at a constant velocity?
Oh, thank you. Okay. We need to talk about this one together. This is a really, really important question that often comes up in science questions, okay, in science classes. Okay, so look at this right here. You can see my screen right now, I think, can't you? All right, so see this? F net equals MA. All right, so F net equals MA. This is Newton's second law, which basically says if there's a force on an object, it's going to accelerate as long as there's a net force. Okay, now see this right here? Constant velocity. Okay, what does acceleration mean? Does that mean to go faster or slower over time?
Or
If something's going at constant velocity, what is the acceleration?
0.
Okay, so look, F net equals MA. So M times 0. What is 0 times anything?
0.
Exactly. So do you realize that what this means is if it's not accelerating, then that means the net force is 0. Do you get that? All right. Now, hey, you're starting to drive. So Brett, are they letting you drive yet? Okay. All right. So let's pretend Brett is driving his car. This is a sweet car, a little boxy car. Let's say Brett is driving his car down Webb Road. And you know what Brett's doing? Brett is going 40 miles an hour, 40 miles an hour, 40 miles an hour, 40 miles an hour. Is he accelerating? No. Mark. Okay. So if he's not accelerating, why does Brett have to keep his foot on the gas? All right. So now think about this. This is the force of the motor. Okay. So if Brett's not accelerating, what's the only reason he has to put his foot on the gas for?
Keep a constant speed.
Because why? What is he fighting?
Inertia.
No.
Friction from the
Friction.
windows.
Friction from something.
That's on,
Hey,
on the ground.
It's from the wind. Yeah, there's a little from the wheels and the ground, but it's the wind. Hey, when you roll your window down, have you ever done this? Have you ever put your hand outside and gone like this in the wind or gone like this and felt it blow you back? Right? So you guys realize the only reason you have to put your foot on the gas is to overcome the force of air friction. Okay? That's all you have to do. Hey, guess what? Gas is like really cheap right now. It's like I bought it the other day for $1.45 at Sam's. That's so cheap, you guys. But out in California, it's still like $5 a gallon. Okay? So think about this. If you lived out in California, would you rather drive a truck like this or a sleek car like this? Which would be better?
Prius.
Looks like
Okay, like a Prius electric. See, watch this. See this right here? The air just goes right over this. Well, when the air hits this, it goes boink like that. It bounces. So do you think a sleek aerodynamic car saves a whole bunch of money? Okay, hey, I got another question for you. The moon. The moon didn't have any air, right? So let's say Case K was an astronaut and he went to the moon and he got on his little lunar rover and he started going in a straight line. Does he need to keep his foot on the gas? Would he just keep going and going and going and going forever? He would, assuming that it was flat and there wasn't any air, there wasn't any friction with the bearings and the wheels. It would just keep going and going because see, there's no air friction. You get that? It's kind of like being in outer space. So here's the main idea. This is a big idea. See this? If it's a constant velocity, acceleration is 0. That means the net force is 0. Okay? Now that could mean something is at rest, or that could mean something is constantly moving and not accelerating. Okay? Now the next one also is important. All right, well, the next couple. What is anybody, let me see, Darcel, what is meant by free fall?
like when there's no, like when you're not like stopping, when you're just like, you keep accelerating down.
Okay, you keep accelerating down because there's no what fighting you?
Air friction.
Air friction. That's right. So on this one right here, say no air friction on number 2. Number 3 is an interesting one too. Here, let's look at this. I'm going to draw an apple if I can. Oops. That's not an apple. All right. So I'm going to draw me an apple here. That's not an apple. Okay, it says in this question, what is the force on a freely falling 10 Newton object, like an apple? My word is messing up. So anyway, hey, if it's 10 Newtons, okay, and it's freely falling, okay, what's the force on it? It would be 10 Newtons. Okay, my computer's acting up a little bit. It might shut off here in a minute with my Google, so be ready for that if that happens. Okay, hey, look at this. Let's say this calculator was 10 Newtons. How come it's not falling?
Another force is acting upon it.
Good. How hard am I pushing up?
10 newtons.
Exactly. See, so look, is this equilibrium right here? See, this would be equilibrium because I'm pushing up with 10 newtons and the calculator is pushing down with 10 newtons. Okay? All right. Now, hey, let me show you another thing here too. This next thing, like I said, my thing is not working very well right now. This Word document isn't. Okay, so Galileo was the one who figured out that all things fall at the same rate. So let me show you this here. If this is working, hopefully. My Word periodically does this. Okay, let's see if this is working. It is. Okay, Galileo, he was a smart aleck. He really, really was. Okay, and he wrote this book. You know, Galileo almost got burned at the stake. Did you know that? Okay, so he wrote this book and he made fun of all the people that believed in Aristotle, which were the religious leaders of the day. Okay, and one of the things he made fun of them is with this little brick thing that I'm just showing you here. He said, all you people that believe that things that are twice as heavy fall twice as fast, you're so stupid. And he really made fun of them a lot. And he said, here, look at this experiment. If I had a brick, and this brick, here we go, don't mess up. Okay, here I got this brick right here. I'm gonna color my bricks just for fun. If I drop this brick, wouldn't this brick fall? And he said, of course it would fall. Okay, and it would fall at a certain rate. Now, if the brick had a mass m, it would fall, you know, just like you would think it would be. And then he said, hey, what if I had 2 bricks? If I dropped them right next to each other, if they're both the same kind of brick, wouldn't they both fall at the same rate? And everybody said, yeah, of course. And then he goes, okay, all you guys that think that something's twice as heavy falls twice as fast, what if I do this? What if I just tie the bricks together? If I tie the bricks together, isn't it twice as heavy? Would 2 bricks tied together fall twice as fast as 1 brick by itself?
No.
No, that's stupid, isn't it? See, he was making fun of all these religious leaders back then by doing this. He wrote this in a book. For this, they almost burned him at the stake, this and the whole orbit thing. Now watch, look at this. F equals ma. Solve that for a. A is equal to what?
Acceleration.
Acceleration wouldn't be equal to F divided by m. Okay, so look at this one right here. Wouldn't the acceleration just be the force of weight divided by m? Now look for this setup right here. Wouldn't the acceleration, now here you're gonna have a chance to say something. Isn't there twice as much force? So isn't the acceleration just 2f, but there's twice as much mass over 2m? Does anybody see what to do?
Doesn't the 2 cancel out? So it's just
Ex-
A equals F.
You're right. Good. See, the 2's cancel out, don't they? See how those two things are exactly the same? You guys get it? See, so it doesn't matter if something's twice as massive as something else. They should fall exactly the same rate, because the thing that's twice as massive, it has twice as much inertia. It doesn't want to fall. You get that? Even though the Earth is pulling on it twice as hard, it doesn't want to fall. So that means it's going to fall at the same rate as the thing that's lighter. So if I have a big person and a little person standing next to each other, and they jump off the stage where there's not going to be much air friction, they'll hit the ground at the exact same time, because the big person's like the 2 bricks and the little person's like the 1 brick. Do you understand? Okay, let me see how much time we've got. It's 10. Okay, we're almost out of time right here. Okay, so I tell you what, let's do. Instead of finishing this, let's make sure you don't have any questions, okay? So you have 2 assignments that I've told you that were due. There's the graph thing is due today. The video thing for the rubber band is due on Friday. And now also there's one more, and now the lunar lander thing, okay? That's due on Friday. How many points do you have to score to be able to get an A?
75.
75, okay? So some of you are going to be like really frustrated with this, okay? I'm going to tell you a secret right now. There's this big cliff thing that looks like this. And then there's a rock right there. It's like a mountain. And then right here, if you land right there, it's to the right on Lunar Lander. If you land right there, that'll get you 50 points right there. Okay? All you need is 75.
Is it in Schoology?
What, the Lunar Lander thing?
Yeah.
No, I sent you a document and it has, let me show you. This document has the website on it, okay?
No, like where we turn the thing in, not the actual website.
Yeah, you'll turn the, you'll just turn this score sheet right in here, on Schoology, okay?
Okay.
Okay, so you're gonna write your score down there. You're gonna testify that you did not cheat and use somebody else's score, okay? And here's the website right here, okay? If you're totally frustrated, who's good at this? Carter, you're pretty good at this, aren't you?
I'm fine at it, I guess. Yeah.
Didn't you score really high before, over 200 points?
Yeah, I think I'm on. I actually have a picture of it's 210.
We'll do it again, okay? Show that you can do it. All right, so you guys, if you need some help, you can ask somebody like Carter or somebody else that's good at this, and you can say, hey, where's some good spots where I can get some points, okay? Who knows, maybe you'll turn into an astronaut someday. All right, I'll see you guys later. Have a good day.
See ya.
See you later, bye.
Hi,
See you later, bye.
Bye, thank you.
Thank you.
Pro gamer, I got 210 on Lunar Lander. Bye, Mr. Holland.
Goodbye.